Hello. In this video, we're going to cover the AVL tree in Java. So what is an AVL tree? An AVL tree is a height-balanced binary search tree. So what does that even mean? Okay, let's say I'm having a binary search tree of this element. I'm sitting in this order. 1, 2, 3, 4, 5. Okay, well, the first node that we insert is our root. So here's 1. Then we're going to insert a child. 2 is bigger than 1, so it should be the right child. 2. Okay, 3 is bigger than 2, which should be that one's right child. 3. 4 is bigger than 3, should be that one's right child. 4. And 5 is bigger than 4, so it should be that one's right child. Okay, so then think, right? What is this, right? What have we actually formed here? This doesn't look like that binary search tree that has log-in complexity. This actually is a linked list now. It's a linked list. And in linked lists, adding and then removing, searching, they're all big O of n. And that makes sense, right? Because if I want to remove 5, I have to go through the whole list, right? So worst case scenario, you travel the entire tree, right? But it's not good at all. The whole reason we use binary search trees is because they provide us with O log n of this functionality, and they can have some order, which hash maps, hash sets, you don't have order, but they provide that sometimes. Anyways, right? This is what we want. so we need some way to balance this tree, right? Because we only get this O log of n when a tree looks somewhat balanced, right? You have some nodes here, like this, and then so on and so forth. It doesn't have to be complete binary tree. This needs to be balanced. Well, this is complete, but it doesn't have to be a full binary tree. This has to be balanced, right? Right. So we want a balanced tree, and sorry. So you want a balanced tree, something like this. I'll make it full. So we can get all this O log n functionality. With simple binary search tree, you have the possibility of worst time case O of n, right? That's why you have a concept such as the AVL tree. An AVL tree balances the binary search tree by height. So we have this idea of the balance factor. The balance factor is the left height of some node minus the right height of some node. So while I'm looking at 30, the left height of 30 is going to be all the amount of nodes we hit before we reach the end, right? Before we reach root. Or I guess including root, before we reach null, I should say. Or you can also view it like this. Right. Either way works. We talked about height in the last video. Or you could count the number of edges from root to leaf. You can do either things. Regardless, you'll find that the left height is 1, 2. It's going to be 2. Right height is 1, 2. Going to be 2. It's not 1, 2, 3. It's not 1, 2, 3. No, it's just 1, 2. Or look at this: 1, 2, 1, 2, 1, 2. Regardless, your left height is 2. Your right height is. And the reason we say 2 is height is the full. It's kind of the furthest you can go. So if I had this 25, well, that's 1, 2, 3. Our left height is now 3. And our height is 2. And because on this side, if I go left here, how much far can I go? How many edges can I count? 1 edge, 2 edge, 3 edge maximum, that's our left height. Right height, how many edges can I count? 1 edge, 2 edge maximum, that's our right height. So in a AVL tree, your balance factors can either be 1, 0, or -1. And so 1 means we're a bit left heavy. Because think about it, right? If left height minus right height, then if we have a positive number, left height must be greater than right height. This means neither heavy, and then this means right heavy. They're fine though. Where we run into issues is when we have a balance factor of 2. So you can never get 3, 4, 5. If you're getting that, you are inserting elements into your AVL tree incorrectly. At worst, you can have a balance factor of 2. So this represents the imbalance situation. Somewhere along the line, we have inserted or we have removed a node that's caused our balance factors or the height of the left and right trees to result in some huge imbalance, right? So 2, this could be 3, this could be 1, this could be 2, this could be 0. Or you could also have negative 2. This could also be negative 2. This can be 0, this can be 2, this could be 3, this could be 1. And okay, so this might be confusing. I'm using 3 here. The balance factor can never be 3, but your height could be 3. They're different concepts. If we get 2, if we get negative 2, we have an imbalance in our tree and we need to fix it with a concept called rotation. So let's go over the rotation. So first idea is left-left rotation. So looking at balance factor, this node here has a balance factor of 0. This node here has one edge on the left, 0 edges to the right, has a balance factor of 1. This node here has one edge, 2 edge, has a height of 2. So when we're coding this, we'll probably just store the height somewhere. It'll be another property of our. But look, boom, 2. Uh-oh, we have an imbalance. How was this imbalance caused? Because we had 2 left nodes, so one left and another left. So we call it the left-left imbalance, or left-left rotation. We have a left-left imbalance, so we solve that with a left-left rotation. So what is that? Imagine ABC as a thread. You have a little tail here, skin or something. I don't know, regardless. We're gonna pull on that tail until so we're gonna pull down there just a little bit until our tree will look like this, right? So you can imagine a thread. If you pull on the thread, you'll get this shape. Leaf nodes have a balance of 0 because they have no children. For B, your maximum height, left height is 1 edge, right height 1 edge, 1 minus 1, 0. Gonna be 0, right? So now everything's balanced. You can kind of view left as we have a huge, heavy, not just a heavy, but like an absolutely massive left imbalance here. So we need to resolve that by trying to pull down here, making our right height bigger. Kind of intuition you can use to think about that. Left-right rotation, same idea. We have a left-right imbalance. How? Let me show you. So no, root has a balance factor of 0. A has one right edge, 0 left edge, so -1. C has one edge, 2 edge, at root, so it's gonna have a left height of 2. No right height, it's just gonna be 2. No, right, wasn't that a little weird? I'm not going left and left. No, remember left height is your height is like, we're calling this left height because it's just the number of edges, it's the maximum number of edges that we take until we reach the leaf node. Okay, the maximum amount of edges. Let's actually dive into that a little bit more. I think that's still, I don't think I'm explaining it well. That's what I'm trying to get at. Let's have just normal tree of like 15. That's a horrid 15, but I think it'll do for now. 12. 10. So I can say this has a balance factor of 0, because it has no children. This has a right height of 1, because 1 edge until we reach a leaf node, so it's going to be 1. and this has a height of 2 because it's 1, 2 edges until we reach a leaf node. Okay, don't worry about the imbalance. What if I did this? Then what if I did this? So this would be 7. This would be like 5 or something. Well, actually, that can't be 5. That could be like 9. Right. Okay. So now what happens to our balance factors? Well, okay, 10 is still 0 because nothing changes. Leaf nodes are also a balance factor 0. This is 0. Our 7 is going to have a balance factor of -1, right? It has one edge to leaf node here. No edges or anything here, so that's -1. 12 is going to have two edges till we reach leaf node. 2 minus, then 1 edge until we reach leaf node. So it's going to have a balance factor of 1. 15 is going to have a 1 balance factor, 1, 2, 3, 1. Oh, it's going to look like this. Oh, sorry, no. It's just going to be like this. 1, 2, 3. I think here's going to have a balance factor of 3. And this will actually never happen in a normal binary, in a AVL tree. This is an impossible situation. You would have done rotation somewhere along the lines here. Yeah, everything's right. But I want to do a situation to show you one idea. Is we're going to the lowest level we can. Okay, you're saying Sid, stop at the lowest height we can. No, lowest level is right. Yeah, lowest level we can go. So lowest level we can go. And if you're confused on what level is, watch our binary search tree video. I'm everything Sid, okay, what does this even mean? 0, 7, 12. Or, well, you told me before, we just go to the node, right? Or we go to the leaf. Well, there's a leaf here. Why isn't the height 1, 2, 2, and then we just say it's 2 minus 0 is 2? Well, because we go to the maximum. We go to the lowest leaf, if that makes sense. The lowest leaf in the subtree. Right? So 1, 2, 3, not 1, 2, 1, 2, 3. Okay, still then left our rotation. That's all I'm saying. Hopefully you understand height a little bit better now. Right? -1, height is 0, -1, 2. So what we do in left rotation, LR rotation, we have a LR imbalance, right? Left child, then right child. You can we pull this child here, pull it up, and then we perform LL rotation. Some people call this double rotation. That's also another trick that we can do, because if you look at this, it's just ABC, right? You can also kind of view LR rotation as this. So we have one node, we have another node. Taking this node, putting it here, taking this node and making it as child. That's also LR rotation. So you can do it this way, or you can do it this way. Both ways work. Okay, R rotation. So now we have our tree looking like this. Balance factor of 0, balance factor of -1, balance factor of -2, right? Nothing here but 2 edges till we reach the lowest leaf. That's going to be -2. Now we have to pull on this side, right? We're going to pull on this side. If here we pull on this side, let's flip it, pull on this side now. We're going to have balance factor 0, 0, 0. Okay, cool. Right, this one, right heavy, left not heavy. So we're going to pull to make left and right balance. Okay, RL rotation, final rotation, right right child and left child with an RL imbalance. I think I maybe forgot to say that this one's an RR imbalance. I can add that right now. This is what we call an RR imbalance. Right child imbalance. So we have this situation, just 0, 1, then -2, because again, nothing here but 2 edges here, -2. We're gonna pull up, we're gonna pull this up, and then we're gonna, so that we can be in a situation for RR rotation. And then we're gonna pull B down to fix it. Or you can also just view it like this. So this node will go up here, and then this node will come down here. Alright, so that is, alright, you can see that exact idea happening. C becomes a parent, the old parent moves down. Or grandparent, I should say. Okay, so those are the 4 rotations, and why am I bringing them up? Because whenever we insert elements, we have to ensure that we are not imbalancing our tree in any way, shape, form. So let's go through some examples. I have this tree. Okay, this will be 40, this will be 30, this will be 35, and this can be 25. This will be 50, and then this will be 60. Right, let's check balance factors. This is 0, this is 0, this is 0, because left, one edge, 1, 2, so it's going to be 2 minus 1, 2 to 2, 0. This one is going to be -1, this is going to be 0. So a little bit of an imbalance here. If we wanted to have a case, maybe I want this to be a little bit weirder. Let's add in a child here. Will that cook everything? I guess it will. If we do this and now this, and then we should be fine here. 40, 45. Oh, 40 already this, we cannot do that. Uh, 48. So 0, 0, okay. I'm going to insert the value of 12. Okay, 12. Okay, so I want to insert 12 into my AVL tree. First, excuse me, let's find where 12 should go. So we're going to compare 12 with 40. 12 is less than 40, so maybe let's set it to its left child of 40, right? But hey, there is a left child of 40, so we can't do that. Let's compare 12 with 30. Well, 12 is less than 30. Move down, maybe it can be the left child of 30. But wait, there's a left child of 30, which is 25. Let's compare 12 and 25. Okay, 12 is left. It can be the left child of 25. Is there a left child of 25? No. So we can insert 12 here. Okay, so that was insertion, but remember, we have to handle. So remember, it's not just insertion that matters. Like this is fine, insert in the right place, but now we need to update the balance factors and see if we went off balance, if we have an imbalance. So I will erase all of this. And now let's recalculate. So this is going to have a balance factor of 0. This is going to have a balance factor of 0. There are leaves. This is going to have a balance factor of 1. This is a leaf 2, so 0, 1, 2, and 1. Balance factor of 1. Let's go here. 45 is going to have a balance factor of -1. 60 is another leaf. It's going to have a balance factor of 0. 50 is going to have a balance factor of 1, 2, 1, 1. Then we have 1, 2, 3. 1, 2, 3. Right, erase this. A balance factor is 0. So inserting 12, we found that inserting 12 doesn't modify anything. We basically just went up, checked that I modified the balance factors here. Went up, should have modified the balance factors here. We're gonna objective and modify the balance factors here. And you'll actually notice something, that this is the same, this is the same, this is the same, this is the same, this is the same. Right? Because those don't change. The only thing that could change is this direct, the ancestor route to the root node is what could change. Okay. Now I'm going to add in, let's add in 8. Okay. So I'm going to erase all the arrows. And now let's add in 8. Okay, 8. Is 8 less than 40? No. 8 is, or is 8 less than 40? Yes. Okay. Maybe 8 can be the left child of 40. No, it can't. We have 30 there. Is 8 less than 30? Yes, it is. Maybe it can be the left child of 30. No, it can't. We have 25 there. Okay, maybe 8 can be the left child of 25. No, it can't. We have 12 there. Can 8 be the left child of 12? Yes, it can, because nothing is there. So we're simply going to insert 8, just like that. Alright, now let's update our balance factors, and we only are going to worry, I'm only going to erase this one, this one, this one, and this one, because we said only the direct ancestral line can be changed. Okay, that has a balance factor of 0, that has a balance factor of 1, 1, 2, 2, and so this should have a balance factor, or so no, we stop here. Okay, wait, we found a balance factor of 2 and are updating. So what do? Okay. Oh, we found a balance factor of 2, so we're going to perform LL rotation, right? Why LL rotation? When we're going up, we went, this is L, this is L, right? You can see in the tree LL rotation, and if not, you can also simply use balance factors. This balance factor is a positive 2, which means we have a 2 minus 0, right? So, or otherwise you can look at this saying LL. And that's not entirely the case, but I want us to look at things through the view of the balance factor. So let's look at it like this, because I don't like what I just said. Because then RL exists, and then RL like left LR exists. Okay, that's 2. Fine. This is 1. Okay, so that's how you notice it's going to be LL rotation. So LL, we have a balance factor of 2, and then R, which means obviously check left child, because it's some sort of either left, left, or left R. Well, this one has a balance factor of 1. Okay, then you know you have left, left rotation. Or left, left imbalance. Okay, let's do that. Left, left imbalance. Take these nodes. We're gonna pull here. Right, and so LR rotation, you simply pull here. This will become 12. This will become 25. This will stay 8. So 825 will have a new height or bounce factor of 0. Then 12 will have a height of 1, which coincidentally is also its balance factor in this case, which will be 1. Moving on to 30, so that's 1, 2, 1. Balance factor of 1, 1, 2, 1. Moving on to this one, 1, 2, 3, 1, 2, 3. Still balance factor of 0. And so we've resolved this rotation issue. Okay. So I've inserted this node now, right? Let's keep going. Because I would like to insert 32. So insert 12, then 8. Now let me insert 32. Okay. delete this. We're gonna delete this. This can go. This can go. 32 compare that to 40. Okay. 32 is less than 40. Can it be? Then we should make it the left child of 40, right? Well, no, we can't because 30 is already there. Compare 32 with 30. Is 30 bigger than 32? Yes, it is. Okay. Let's try and make 32 the right child of 30. Well, no, we can't do that either because 35 exists. Is 32 bigger than 35? No. So let's make it the left child of 35. Can we do that? Yes, because it is simply null there. Right, this is just simply the insertion that we did in the last video. Because this is still a binary, so it's tree only. Well, the only new aspect is that we have to include balancing now. Okay. Okay. Anyway, sorry. I got a little bit distracted. So let's talk about this now, okay? Let's check all the way up from here to root. So direct ancestry line. This one, and then this one. So firstly, this is going to have a balance factor of 0. It's going to have a balance factor of 1, 1, 2, 1, 2, 0, 1, 2, 3, 1, 2, 3, balance factor of 0. So I can insert 32, nothing will happen to our program, or no rotation needs to be done. Let's insert now 34. Let's insert 34. Let's see what will happen. So I'm going to insert 34. So I'm not going to repeat that same check process. We've done it for the first tree. Where will 34 end up? 34 will end up right here. Now let's evaluate our balance factors. Well, this is going to have a balance factors. And I'll just erase these because they're going to be reset. And I'm drawing balance factors. You don't get the idea that we're actually storing balance factors with anything. The balance factor of a node, we're gonna store the heights when we code this, and then we'll just use that to determine balance factor. The balance factor is not a property of a node. The only special thing in AVLs is height becomes a property of a node. Okay, 34 is going to be inserted, right? And I'll erase all of this stuff. So then we need to evaluate all of our balance factors up to ancestor. 34 has a balance factor of 0. 32 has a balance factor of -1. 1, 2, nothing here, so a balance factor of 2. Okay, so now we have a issue. And this is what issue? It is a left-right issue. Left child, right child. So this is an LR imbalance. It needs to be solved with LR rotation. Let's look at that part specifically in the tree. So I have 35. Then I have 32. And I have 34. So we have an imbalance here. So what do we do with LR imbalance? Well, we can do this process, right, of double rotation. I'm simply just gonna do it the shortcut cheating way, which can go here. Again, just taking the 34, bringing it up to as the parent, and then dropping 35 down here. So what will that mean for our tree? 34 will be up here. 35 will be down here. And then 32 will be over here. And this may seem complicated. Rotations will simply just change pointers around, so I don't think it'll be that bad in terms of actually programming it. So let's replace that. Delete you, delete you, delete you, delete you. And then so our new structure is going to look like this. 34, 32, right? Balance factor 0, balance factor 0, balance factor 0. So then we'll just do balance factor 1, 2, 1, 2, balance factor 0, 1, 2, 1, 2, 3, 1, 2, 3, balance factor 0. So everything is balanced still. One thing I want to bring up, one point is rotation will happen with the node that is imbalanced, then that node's child, and then like its corresponding place, right? Like this one, this was imbalanced. First we know it's 2, okay, so then simply go here, 32. The -1 tells us we need to move on to the right node. So I'll go to this right node, and then that'll be our third node for rotation. If somewhere along here it caused some balance factor like this to be 2, don't think that means we're going to reevaluate everything in this path. Simply just be this node, or this node, and then depending on whether it's just 1 or -1, where it goes and such. So I just have in my notes when is LL away, LR away, such and so forth. Okay. And if there is an imbalance, this won't be 0. This will be 1 or -1. Yeah, it will not become 0. I don't think so anyways. If it does, correct me in the comments. I am learning this, so I wouldn't say I'm no like master or anything of AVL binary trees. Anyways, let's move on to 54. So I want to insert 54 into my tree. Where is that? That'll be right here. I'll just go like this and say 54. The left child of 54. You know, I'm not gonna do that. That's very confusing. Delete you. I'll go here and I'll say 54 is going to be here. You're still 0, and if you're confused where you have these lines, I just did the lines so that nothing is changing here when we're editing here. Same thing, these ones won't change. Well, these ones will change. I'll remove the line though. Like, because what balance factors get updated? The ones from the uh, newly inserted leaf node all the way up the ancestors. And all the ancestors. This is not 2. This is 0. I think I had 2 there as that example. Okay, let's do 54. Balance factor 0. Left child, balance factor of 1. I guess even here it's not clearly left, but it's okay, it's okay. Get that with an L. 1, 2, no, right, 2 right children, 2 left children. Balance factor 0. 1, 2, 3. 1, 2, 3. Balance factor 0. So we can insert 54 just fine. Let's insert 58. So 58 will come down and become this node's right child. So yeah, take this stuff. Simply move it like here. I want you to be able to, this is a little confusing the way I've drawn it. Okay, I think that makes it clear that that's its left child now. I'm happy with that. So now let's evaluate balance factors again. 58 is leaf, balance factor is 0. 54, 1 edge, balance factor of 1. 60, 1, 2, nothing here, balance factor of 2. Okay, then we need to perform some rotation to fix this. Let's do that. Loki was trying to get us to have an. We'll have an LRR example right after this one. Maybe, I don't know, because you're gonna balance it right now, so we'll see what happens. This is, what is this? Is this L though? No, this is another LR rotation. I've already shown that. Let's just update the tree. This will become what? This will become 58. Before that, how do I know it's LR? This is 2, which signifies we have a left imbalance. So we're going to move to left child. This is 1, which signifies, sorry, this is -1, which signifies we need to move on to the right child. LR imbalance. There we go. I explained that for LL. I did not explain that for LR. That's the explanation. Explanation is important because that's how we're going to be able to um, do this. That's very important for the coding portion of this section. So what was it? 60, 54, 58. This will become 58. This will become 54. This will become 60. Alright, just your LR, normal rotation. And then this one will still exist, but it's here now. So 54, 58, and 60. So let's evaluate this line up. This one is going to be 0. And remember, when we're evaluating, we're not really like checking anything. This will be 0, this will be 0. This is what? This will be 0. This is going to be 1, 2, 1, 2, 0, 1, 2, 3, 1, 2, 3. So everything is good, everything is still balanced. For the last one I shall insert, I will be inserting, I want to insert a 59. Where will that go if 59 is bigger than 60, or 58 is bigger than 50, or sorry, 59 is bigger than 58, less than 60, so then here we'll have 59, right? This will be 0, this will become a 1. Let me do that. This will become a 1. This will stay 1, 1, 2. This will have a left or a right leaning imbalance of -1. This will have 1, 2, 1, 2, 3. Right leaning imbalance of -1. This will have 1, 2, 3, 4, 1, 2, 3. Right leaning imbalance of -1, 3, so. Let's move on to deletion because we spent a long time on deletion. So RL deletion. Well, let's first look at some examples. So there's an idea of 6 cases here. L1, L-1, L0, and then we can have R1, R-1, and then R of 0. So what does L1 mean? L1 deletion is this. So I have my tree. It has this child, it has this child, and then it has this child. And an idea you might understand is that this balance factor will have 1, and when you delete a node, it'll become imbalanced. So when your balance factor is 1, and then you're deleting a node, typically balance factor will become imbalanced. I think, I don't know, that might be a generalization I made, that's wrong. 0, 0, just have balance factor of 1, just have balance factor of 0, right? Or of simply 1. Okay, I'll say bye to this node. It goes away, we're deleting it. Well, now I can have this. There will be no more right, so this will become a balance factor of 2. So How do we resolve this? Well, what is this? This is what? Simply LL rotation. So we were going to do LL rotation in this case, and then we'll have solved it. I'm not going to go over the LL rotation because we've done a lot of LL rotation there. Okay, next one is L1 deletion, or L negative 1 deletion. So my tree is looking like this. Balance factor 0, balance factor 0, balance factor negative 1, 1, 2, 1, balance factor of 1. Right? I'm going to delete this node. What will happen? This will become balance factor of 2. What is this case? 2, negative 1, 0. What is that? That will cause LR rotation. So how do we solve this? Simply LR rotation. And it'll be solved. Okay, what about if we did L0 deletion? L0, what does that mean? This, 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 0, 0, 0, 0, 1, 2, 1, 1. I'm going to delete this one. Balance factor becomes 2. Because it's there, you can choose if you want to do L1 deletion, choose if you want to do L negative 1. In our case, I'll just do L1, so I'll say L rotation. Okay, moving down to the R's. So R1 was in the name. So your right child, right child of a balance factor of 1, 0, 0. So be leaning negative 1. Delete this, become negative 2. Well, what is this? Negative 2, 1, 0. This is RL. RL rotation. So we'll perform RL rotation onto this. R negative 1. Okay, this is what I treat like this, like this, like this, like this. So this is 0, this is 0, this is negative 1, this is negative 1. I'll delete this. This will become negative 2. Our right child has a balance factor of negative 1. What's this deletion case though? What is this rotation? Sorry. R rotation, right? Whenever we have this situation, it's R rotation. If you're confused how I'm getting to these rotations so quickly, well, we explained them here, right? Negative 2, negative 1, 0. Negative 2, 1, 0. That is where this is all coming from. And then R0 is the same thing as L0, right? Your tree will look something like this, or the subtree, whichever you're trying to delete will look something like this, like 0, 0, 0, 0, 0, and then this would actually be negative 1, not 0, because that has a height of 2, that has a height of left height 1, right height 2, so this will be negative 1. Okay, let's delete this now. This will become negative 2. And here you can choose RL or RR rotation. So you can choose between either R1 deletion or negative 1 deletion. It's simple. It's all just rotation. All of this is just rotation. Right? Insertion just the same as binary but rotation. So then what does that mean? Deletion is also going to be the same as binary but rotation. So we'd have a case 1, we'd have a case 2, and we'd have a case 3 just like we did in binary. Right? Leaf node, just delete it. Case 2, what we said in binary. The node you're trying to delete has a child. Delete this, make that child the new left node. That's really what's gonna happen. And garbage collection will come and sweep that up. Wait, bro's low-key mad sad. It is most of it we get the child. The child will not be able to get to him, so it's irrelevant. But you cannot climb up a tree, only down a tree. Case 3, you have 2 children. I'm trying to delete this node right here. Or let's do it like this, actually, it's a little bit more interesting. Boom, boom, I want to delete this node. So we do normal deletion, right? This would be in order predecessor, in order successor. I'll say in order PS, I'll say the in order predecessor will come to take its place. It takes this, it just replaces the value, okay? It just replaces the value. This gets deleted in actuality. The reason we can just do that, replacing the values, because we want the pointers to stay. We want this, we still want this connection, and if we made the new node, if we replace this node with this node, oh, what's the right child of this? Null. So then our right child become null. So we're just replacing the value with this P, and this would become a S. I just love this. But look, is this tree, which would be perfectly fine in VST, allowed in AVL? That's 0. That's -1. That's +2. So no. So just as how in insertion we inserted then we rotated to fix balances, in deletion we do the same cases that we've learned in binary search tree, and then we perform rotation right after to fix imbalance. Okay. So this is what you need to know for the AVL tree. Now let's code our own. I'm in this program. Inside of sources, I'll create a new AVL tree. Okay. In fact, I might just want to call it. Can I just call it AVL, or I'll call it AVL tree? Man, but AVL sounds cooler. To AVL. Okay, cool. So now we have this. It's AVL. That's fine. That's nifty. Okay. Okay, let's get the code in it now. We're going to need to create a class inside of here, which I'll call input class. You know, I still never made that video on final classes or inner classes. I've been meaning to make that video for like a bajillion years. That's crazy. I thought I would have made it by now. I guess I haven't recorded it yet. It's kind of a problem. I probably should record it. I think I have final classes recorded. It's not AVL or not. You know, I don't know. It's been so long. Okay. Um, what does our node need? It needs a right pointer. It needs a left pointer. It needs some data which we int. Now, AVL specific. Let's store the height. So public node. We still will just take in the data. Okay. This dot data we can set the data. This dot right will be null. This dot left will be null. And what is this? This is a null or leaf node, right? When it's right and left children are null. What is the height of a leaf node? The height of a leaf node is 0. So this will become 0. Okay. Let's create our node root. We still care about this guy because it's still just a binary. This is the binary search tree, just with height balancing, right? So I'll create my public AVL. assign this dot root to be null. Yeah, this will be fine. Public void insert. We'll take in some int data. And make this a node insert. And I don't care about returning node root. Public, we'll say root is equal to insert root, and we just won't return anything. Public node insert. So this one's going to be our private one. I'm going to call this our help. This is kind of like a helper function. Not really helper. This is the one that's going to do all the heavy lifting. Node and data. Right, same idea. What do we need to do first? Well, we need to find where we can insert this node. So we're going to do if n. First we say if n is equal to null. Then we want to return null. We'll actually want to turn new node with the data. That's the correct approach. This will take care of if the root is null too. It's cool. If our if the node that we're looking at, if it's left, or if its data is greater than the data stored in this value, then we want our data to be inserted as a left child of this node. So I can say n.left is equal to insert and left comma data. So what it's going to do is it's going to try and insert the data at this guy's left child. Else if n.data is less than data, n.right in this case, we're saying now the data we're trying to insert is bigger than the data in this node, and it makes sense this to be the node's right child. So we're going to do this, and this line is simply just going to try and insert it in as this guy's right child. So if they are the same, return n. And so I can remove this. Now, this is standard for a binary tree. This is the standard for a binary search tree. Excuse me, but we're building not a binary search tree, we're building an AVL tree. So what is it? Whenever we need to insert, we need to check for the balance. So here we've inserted, right? So we finished inserting our no. Oh, I understand now. Right? Where do nodes get inserted? Always adds the leaf. So in here, we need to handle rotation. Okay, do I want to handle rotation there? Okay, first thing I'm thinking is maybe just here saying n.left.height plus plus, and then here n.right.height plus plus. Because if we're inserting a node, then the height of this branch will increase regardless. So that actually will just take care of all of the heights for every single node for us. I'm fairly certain that'll be the height handled. Okay, so let's think about this. So when I was adding all these nodes in here, if I first made a point to mention that only this would change, this would change, this would change, and this would change. The balance factor is here. Currently, I don't have a method of getting the balance, and we don't have to worry about doing that because recursively it'll update. So let's focus at the microscopic level. Just get the balance factor of this, for instance. Now let's just get the balance factor of where we currently are, which is this 8. But then if we're going up recursively, then it doesn't make sense for me to put handling rotation in here. So handling rotation, I think, should happen right here. Because we will insert the node, we'll check, we'll calculate balance factor, so on and so forth. If everything is good, balance factor is 0. Then move up to the next one. Check, everything good, move up to the next one. Calculate balance factor. Yes, I think handling rotation here is the right idea. Because if we handle it here, it's not going to happen for every node. It's only going to handle the rotation. It's only going to validate the balance factor of this last node, which is not really what we want. We want it to evaluate the whole ancestry tree, which can just be done by letting rotation do its job. Or by letting it recursion do its job. Okay, so what do we need? I need to get the balance factor of some nodes. So say balance factor of this node n. I'll create a private int balance factor. It'll take in a node n. So what do we say balance factor? So n dot return n dot left dot height minus n dot right dot height. Right? Take the left child, take the right child. So for a root node, this will be 0. If balance factor is 0, well, if it's 0, -1, 1, we don't care. Or we should care, because thinking about it logically here. If balance factor is 0, we'll simply just return n and move on with our day. If balance factor is equal to 1, oh yeah, I think I have an idea. If balance factor is equal to 2, this means we have some left imbalance going on in code. So I want to check if n dot left dot height, or let's actually calculate the balance factor of n dot left dot height. And if this comes up as 1, then this means that we have some left LL imbalance. So we want to do LL rotation. Otherwise, then this can only be LR imbalance. That's why we want to do LR rotation. This should be end of left, not end of left. Let's make a function LL rotation. Perform LL rotation with the node n. We don't need anything else. We just need the node because we'll be able to get the children from the node. This one we can say perform LR rotation with the node n. Else if balance factor is equal to -2. Let me copy this. Say balance factor is equal to -1. It should be n dot right. Then we want to perform RR rotation because we have an RR balance which calls for RR rotation. Otherwise, let's perform an RL. We have an RL imbalance, which means we need an RL rotation. Right, and this makes sense because it's built off of the idea of the balance factor, which I was explaining in the drawing a lecture section of the video. So we have 4 unmade functions. We need to make them private. Just return anything. It's just going to handle some simple operations. And so I'll say this will be node n. So what happens in LL rotation, right? Well, looking at this image in LL rotation, um, the sibling becomes a new parent. The old parent becomes the right child of the sibling, and then their left child of the sibling stays left child of the sibling. So what can we say? We can say n dot right is going to be equal to n. So this will set right child of sibling to parent. Just like we saw will need to happen over here. Just going to pull this down. But what? But what? The left child of parent is still pointing at sibling. At this. It's not good. You don't want that. That's weird. Right? We want our left and right child of our parent node to be free, to be able to have children. Because if this one's caught up on its old child, then it's going to be weird. It's going to cause problems. So I can say this line will be clear parent of right and left responsibilities. So n dot, and sorry, this would be, how do I want to do this? I was thinking n dot left is equal to null, n dot right is equal to null. But this actually causes some sort of issues in our code. Let's see how to fix this. Could you n dot right, and then you want this right pointer of this node to equal to n. And then so can we clear it now? Yes, you can. We can totally clear. We'll clear that connection. Life will be good. But there's one more point I forgot to discuss, or just didn't bring up in general. What if this node? So if this node has children, like child here, for instance, okay, doesn't matter. Let that child come down with it. So then actually, then we wouldn't want to clear its right child that exists. We'd only want to clear its left child. So remove left one, right? Like we wouldn't want this connection. We wouldn't want there to be some left connection here. But if this guy is a right child, then what? We're gonna let him no. We want him to keep his child, keep his children. What if this guy's a right children? Then what's going to happen? Well, because we're assigning this to its right place, now this guy's misplaced. He's sad. But we can't just remove him. Then we're not inserting anything correctly at all. What we can do is if so I will store n dot, so say node displaced is equal to n dot right number. So it's already going to be the right child of the node. And simply make n dot left displaced. Because if it's null, then what? This will be null, everything is happy, we're good. But if there's some child here, then pull it over and make it this child over here. Like he goes from being sad to being a happy little node. Okay. So, and if any children are here, does anything happen? No. They still get to keep their children all intact, all fine. Okay, what if this one has this one? Well, we won't have a case where this is already pre-filled, so this should be good. LR rotation should be handled. In essence, all we're doing is setting the right value of our node to be n. So we're basically just making this right pointer of our. Should it be like this? I made a mistake. This should be n dot left dot right, and this should be n dot left. Right. It's LL rotation. So we're gonna do that. Go there. That will move it over there. I think life is good. Right, and I'm pretty sure it'll be fine. Okay, same idea. LR rotation. Well, not same. All of this is just pointer movement. Pointer movement. Okay, LR rotation. What do we say? Well, we need the left dot right would be left dot right. Ooh, uh-oh. I don't know, this is right. Wait. Okay, so in this case, the left dot right is going to be equal to n. Because now we're saying this child, which is the right child of this, when we're all done and said, this is going to become the right child of this. So this is going to be like this, right? So that's line 1 done. I'll get rid of this. I'll delete you for now. We'll come back to you once I've understood how to actually code this fully. So n dot left dot right will become the parent, correct? Then n dot left dot right dot left should be nothing but n dot left, right? In this left node, it's so here left, right. It's left pointer now. We said we'll point to you, which is all this line is doing in the code. So now we have disconnected. Now we have disconnected, but we still have this issue going on, right? The right pointer of here is still pointing at this. So I'm gonna say displaced. I will leave it as null for now. Now let's work through if they have any children. If this guy has a right child, where does it go? The right child needs to go here. It wouldn't go here. It'd be more like an apple falls from the tree situation. The right child will go there. And the reason for that is, what is this right child? It is C's in-order predecessor. So it should just go there. Okay, and what if we have a scenario where this guy has a child here? This children doesn't matter. This children doesn't matter. It'll go fine with it. If this one has a child, then it'll be this guy's in order successor. So how are we going to code this? So if n dot left, if n dot right dot, sorry, if n dot left dot right is not equal to null, which means we have a child there, displaced child, then we just want to set n dot right, sorry, n dot left equal to n dot left dot right. Lots of pointers, but this is all this is. It's only just simply pointers, and I'm just using this pair. I'm using going off the parent node pointers, right? So that will handle that case for us. And well, we want to save this actually. So I call this maybe node in. The reason we want to save this is because all of this code is going off the old stuff, and if we try and write some new code here, that might mess up. In order pred, so let's say pred is equal to nothing. It's empty at the moment. However, if this is true, let's make this pred. Else if n dot left dot right dot left not equal to null, I can make a node. I'll call it successor, or just suck, and then we'll set suck equal to this. So let's set this new node's left child right? The left or the right child. This will become whatever suck has, and then n dot left, or then n dot right dot left, so whatever Fred has. And then we don't even need this. I'm just going to make this u. And I'm just going to make this u. Because in the instance where the children don't exist, okay, that's fine. It'll just set those values to none, and then life will be good. Because we already know there won't be any values here from here because A was there. And then there can't be any values that might correspond here because B was there. That should be LR rotation. That should be LL rotation. And I think it's right because it corresponds with what we've said in the diagram. A little bit complicated. So I can simplify this. Let's say node parent is equal to n dot left. And so wherever you see n dot left, I'll just make this parent. Parent, 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 parent. Is it n dot left, right? Yeah. You want to do everywhere? Assume become parent. And I think this is fine. And I'll leave it as pointers. I like it this way. I'll leave it like this. This I don't know. This works in my brain better than seeing parents. And also, I don't know if like it could cause any issues with the variables. I don't think it could because we're updating values. Well, I'll be doing something in pointers, but it could cause an issue. Node and how do I want to go about doing this? Well, if I look at RR rotation, it's this case. So then the sibling will become the parent, you'll become its left child, you'll become its right child, so you'll stay. So we can do n dot right dot left is equal to n. So this should just be u, right? Excuse me, this should just be what we're doing here. We're changing it up a bit. So n dot right dot left is equal to n. So that dude I said, this guy's, yeah, this guy's left corner will now be pointing towards this. And however, B will, well, what will A be doing? A's left child will still be preoccupied filling this guy's role in, right? It'll be still be pointing at that. If you have any children here, they stay. If you have any children here, they stay. That's not a problem. If you have any children here, they stay. That's not a problem. Because your right pointer is working. This still it has to be. If I have any children here, which is the only displaceable node because it's filled with that, then what should we do? We'll make that child be this value. Why? Because what is this? This is the in order successor of A. So then it makes sense that it should be going right here. And this will also break that weird connection thingy that we're talking about. So I can simply say and what would this be? And right left should be equal to, wait a minute, no. Well, because I feel like, okay, that's right and right left. Let's set n dot. So then this should be n dot right be equal to n dot. So be equal to displaced. And what is displaced? Displaced would have been this previous value. So it should, if I code it right, it should just be, oh, that seems like I coded this right. It should just be this, but mirrored to this. What is this? Just mirroring of each other. Oh, if I could just use the mirror thing, it might help us with our L rotation. So what do we say RL rotation was? RL rotation was this. Take the right left and make it a new node. So left dot right dot left. Or sorry, left. So to become n dot right dot left. Should become the new node, and what did we say? We said the left child of that should be the old node. It should be n dot right dot left. We'll go here. And then what do we need? That handles this connection. That will push this up here. But we need to set its left child. Or that's really what we just did. We set the left child. We need to set its right child to. So we need to set its old parent to its new right child. That should just be n dot right. So here I'll make this simply n dot right. And then what's that be? That should be n dot left, n dot right dot left gives that dot right. So n dot right dot left dot. So we're seeing here, wait, what's happening? Oh, it's flipping, right? Every value is flipping. Okay, successor then should flip. Predecessor then should flip. Is everything still correct? If I were to add in a itty bitty guy right here, he moves up the chain. Uh-oh, he loses parent. Well, what is he? He's the in order successor, or he's the in order predecessor of D. So he should move here. I know he's a little bit discontent, but hey, what can I say? It's just how it's the living arrangements. This is the in order. So he was the in order predecessor of D, so he'll move there. This guy here is the in order successor of B, so he should move here. So first let's check in order predecessor. We said that was right, left, right. I need to flip these two. So right, left, right, left, right. It's in order predecessor of D. So moving left one, then now which right you can go. And then in order successor of B will be right, left, left. And I'm low-key already noticing a flaw in this, bro. Wait, hold on. Like, look at that. I said left, right, right. Left, right, right. One of those is wrong. LR rotation. Predecessor is going to be what? When you have a child here it becomes like this. So that's left, right, right. That's in order. Predecessor, left, right, right. Okay, everything's good. Is in order successor. So just left, right, left. should be left. Is everything mirroring each other well? Yes. Yep. Okay, cool. So that should be all 4 rotations done. That should be insertion complete. First biggest one, this is wrong and this is wrong. So let me tell you why it is wrong. Well, because look, when do you actually increase your height? It's only when a new node is added, but when will this happen? This will run for every single n elements, right? Because we're going to run this, then we increment height. What if we're going through here, we find the element already exists, right? So we return nothing. But then as we keep coming back, we're going to increase height by 1. That doesn't make any sense. So then height shouldn't implement here. That makes sense. Where should it go then? Where do we implement this fix? Probably here. So what will height be really? Your height should always be like what? It's the height is the max height between your left and right sub. So what does that mean? We can say that n dot height is equal to mat dot max the height of your left subtree and then the height of your right subtree. Well, let's actually make this to a function. So I'll say height and left, height and dot right. So I'll create a function. I can make it up here. Let's call it private int for taking a node n. So if n is equal to null, then we want to return 0. Otherwise, if otherwise, what do we want to return? And height is 0. That makes sense because there was no height there, and a root node, a little leaf, little child node can't have any height. But then I think it's dependent. Oh, no, then it should just be 1. Right? It should end that height. Say. Okay. Right, because should just be 0 though, because I think 0 is fine. We'll leave 0 for now. If I need to fix it, I can fix it later. So this should be your height updated. Well, let's think about it. So will it actually fix our height? So according to the program, let's look at something like this, right? I think I have some room here. So we have this tree. Let's say we're trying to insert 10, 9, 11, 9.5, and it's 8, right? I want to insert 7. We're going to go here, go here. Now we're going to add 7. So we haven't actually implemented like height fixing or changing the height yet, right? Because where is height actually being changed? Not anywhere right now. Well, let's do though. So first we'll just set the height equal to the height of the left child, which is 0, and the height of the right child, which is 0. So what will make this height be? This will have a height of 0, which is right? Yeah, this should be right, because if we're just looking at this, should it be? Where does height start? It goes 0, 1, 2, right? So it's 0. I'm gonna say this is fine. Then, okay, fine, we've done that. Move back up. Okay, whatever. Height of left subtree is 1, 0. Okay, now we can make this 1. Move back up. Height of this is 1, 2. It's 2. Height of this is 1. Oh, that one is magic. This has a height of 2. Moving up This will have a height of 1, 2, 3, so make this tree. And then I think that should do it. I think this is right. Okay. And then conversely, the issue here is that if I notice null, we have nothing to do about it. Height, so this should be the left height minus the right height. The same idea here, although I do kind of like using this a little bit better because it has the null check that we just didn't provide for originally. Okay, and now my rotation is wrong. All rotations are returning node. Okay, why? Why are we returning a node, Sid? Well, it's because, and we set n equal to this. So what is n? N is the imbalanced node at this point of our code. It's the node that has a balance factor of 2. And then it is also the root node. Well, what happens to the root node in this code? Well, we swap stuff around. The root node always changes. We need to actually update that in here, right? We need to find some way to connect it back to the pointers. Return n. It'll go back. It'll update all these pointers. Without doing this, okay, sir, it'll get updated, sir, whatever, right here. But will any of these values of n change in this code? Will this change? Will this have the pointer effect that we want? No. If you're confused on that, you can kind of watch the last video. I think it'll help you understand more about how this return n correlates to these pointers. So simple fix, right? Okay, then turn the root node. But then here in my left rotation is the next problem that we have. Okay, but there still is, actually no. So my pointer logic is correct, but my cloud thing is better. Everything is right. What is our new node? N dot left dot right is our new root. But what am I forgetting? Forgetting all about height. Forgot all about the height modifications when I was writing this code, which is not a good thing to do, considering the whole idea of balance factors relies on the height. Okay, so when we do this, what happens? Well, let's think of it in terms of n. How many, what was your height? 1, okay, it stays 1. What was your height? 1, 2, okay, it stays 2. What was your height? It was 1, 2, 3, okay, it becomes, this becomes simply 1. Okay, how do I determine this? Well, let's say we know this displacement will go here. We know this will be empty. So I'm going to write that n dot height equal to the maximum, of course, the height of our n dot left, comma, the height of our n dot right. Okay, so what is this saying? It's saying this left node, right? This had a height of 1, 2, 3. Well, now it's here. Let's just find the maximum between children, make that its new height. Simply put, that's all we're saying. Okay, that's to handle the updates for the height. And then for height, actually, we'd want this to be what? We want this to be 1 plus. So I'll make this 1 plus. I'll go up here. I'll make this into a 1 plus. And then what does that mean for the function of height? Where did I write that? I wrote it over here. Let's return negative 1. That way, if we're looking at the root node, it still has a height of 0. Otherwise, well, why do you want this 1 plus? Because our height should hopefully be increasing as our tree grows, right? As our tree becomes bigger and bigger and bigger, we want our height to subsequently increase. Right? And then you might be saying, okay, Sid, explain this one a little bit more. I will. Let's dive into this line separately. Explain most of the actual code with this example, so I'm not going to dive into that, but we can dive into this. So I have a tree that looks something like this. I Like this is the best way, in my opinion, to understand this code, visualizing it. 39, I don't know, 42. Okay, this is from random tree. I want this to have a height of 0, this to have a height of 1, this to have a height of 2. 0, height of 1, height of 2. So if this code is correct, this should work. Well, let's see. So starting off with the root node, right? Let's say we're looking at the height of the root node. Well, then what is that? That's the height of this left child, height of this right child. And right now everything's set to 0. So then at a root, well, height's gonna be updated as we insert. So let's say we just are inserting this 8 into the code, right? And we are already all this. Let's actually go by systematically and insert. That is the easiest way for me to explain this code. So 0, just root. We went from empty to inserting 30 to become our root. So then we have no left child, so that's going to be 0, or that's going to be -1. It's going to be -1, maximum, that's -1. -1, 1 plus -1 is 0. I will add in the 15. 15 is added. So consider there, has no left child, so this will have a height of 0. We'll have a height of 0, then what's going to happen here? Well, this is going to have left child height of 0, right child -1, 0 plus -1 is 0, -1, maximum that is 0, so this will become 1. And corrections, you can view height as going from 0, 1, 2, or you can view as going from 0, 1, 2, like root to leaf or leaf to root. I think in coding they do is 0, 1, 2, but for UIL, read it like this. For the code, look like this. Because you can recursion, right? You can only backtrack, you only go back up. Let's insert, so we inserted 15, let's insert 45 now. I'll insert 45 here. So this will have a height of 0, right, from the algorithm. Okay, move back up. Left child of the root has a height of 0, right child has a height of 0, 0 plus 0 is 0, 1. Right, so you can just kind of see that this is working. Now there are a few more things. Let's update you. I mean, this is not wrong, or by any means. I feel like my pointers are right, I think. But this could definitely be a lot cleaner. Okay. So what do we need to do? LR rotation. So in essence, when you look at LR rotation, right? What is LR rotation? LR rotation is this. So we have this situation going on, and what are we doing? When we have this and this, and then we're rotating it, so this pulls down A to B, and then this pulls down, so we have B to A. What's that? Well, that's simply RR rotation, which we've already learned. Here, when we're doing this pull-up motion, so we have C to D, making that D to C, what is that? Well, that's simply LL rotation. So all this code, get out of here. I'm gonna say end up is equal to the RR rotation on end dot left, right? So simply update, do the rotation, get the new left value, update it like that. The pointers will all be fine below. And then return LL rotation on N. So what am I saying here? We're gonna do RR rotation to get this. And then what do we say? This would be, or sorry, LL rotation. And then we're at this step now. So when you do RR rotation, right? This step now, we need to do LL rotation. And then we need to factor in the height too. Copy that. Or actually, we don't need to worry about height because the height gets automatically updated for us. Because what we're calling LLRR rotation, they're gonna handle the heights. LLRR rotation is gonna deal with the heights. Take all of this simply to LL rotation and height, and then return LLRR rotation and okay. And then we also need to fix U, right? Well, okay, this is all right. My pointer stuff is all right. Right, left, right, left, right, and this is me right, left. So everything returns now. Life is good. Insert is good. Well, let us check if insert is good. Okay. This is on me. I did make an issue here. We should probably store this. Why? Because look, we're setting this to this, which is fine. But then what are we doing? We're updating n.left. So this is not this node. It's referring to the displaced right child. It's just going to be null. Same idea here with LL or RR. We're updating dot right. Then we're trying to do this again. It's going to be displaced dot left. That's not what we wanted. I'll create a node called returns equal to n dot right dot left. Ah, the last error. Top dot height changes. Sorry. Return dot height needs to change. Okay, why? Why am I saying this? You understand why n heights change because the children it has changes. Right? This goes from having no kids to possibly 8 children. Right? Or this goes from having 2 children to essentially no children or a displaced child, whatever. Well, what about this one? It goes from having only one child to 2 children. And remember height itself. The issue I was having when I was coding this AVL structure was that I was viewing height as just one value at the very end. Now height needs to be constantly updated because it's all happening recursively. So then even here, even though at the very end, right, at the very end, the total height is the same. I was thinking of things in total height. Each individual height is changes, right? Because look. Okay, yes, LL. Okay, cool. We pull this up. It has new children now, right? Because we have new children now, we have to refactor the height of this node. Simply because stuff in here could change, stuff in here could change. If that stuff were to change, making this one bigger and making this one smaller than here, it caused this one to change, right? So my simplistic example here, you can't really explain that well, but just understand the idea that when the nodes of a children, when the children's nodes, or a node, okay, when the children of a node changes, its height should change too. So what I need here, I need returns left. What is height if not just the maximum height of its children? Same thing for LL rotation. I called it return node. Look at me being fancy. I'll call it return node here. So we've taken care of the heavy lifting with all these rotations. Now that we know our rotations work, insert works, everything is fine. Let us move on to deletion. So take a void, remove int data. Root is going to be equal to remove root comma data. If you're confused on this line, watch the BST video. Public void remove. Okay, node n int data. So how's remove work? First, we need to search for it. So first, I'll just write that quick. If n is equal to null, return null, return a new node with the data. And I'm sorry, this shouldn't be for the speed node. First, let's set up the binary search removal, and we can worry about doing rotations after we have this implemented. What is that? And if n dot data is greater than this current data, then I want to do n dot left equal to remove n dot left comma data. Else, if n dot data is less than data, n dot right is equal to n dot right comma data. Yes, that makes sense. Else, if this is when those three cases have to happen. So if n dot left is equal to null and n dot right is equal to null, let us return null. If n dot left is equal to null, in this case, let us return n dot right. If n dot right is equal to null, let us return n dot left. And then otherwise, if we're still in this code, that means we have two children. An error somewhere. It's saying, am I not returning something in one of these lines? The error is like right. Oh yeah, in this one. So nothing. Okay. So otherwise, let us find the in order predecessor. So I'll say node pred is in order predecessor of pass an n. What do we need to do? We need to set e2 n dot left is equal to remove n dot left, searching for the data on the predecessor. We're just gonna remove the predecessor. We're starting at the left subtree because we need to come once we remove the predecessor, we need to come back and fix all the pointers. And then lastly, n dot data should be equal to dot. And then this is I actually explained this in the video. We're just updating the data. Okay, well we're missing this function. I will create it in order predecessor. We're taking a node of n. It'll return a node. Okay, how are we going to do this? Very simple, very easy. First do node dot left. So node is equal to node dot left. And while node dot right is not equal to null, so while there's a right child, n is equal to n dot right. And then once we reach the case where there's no more right children, we're at a rightmost node. Let's return this. So return n, not n dot right, because that would be null. Let's return n. So this is removal, binary removal. Fairly certain I got everything correct here, except for one thing. Ooh, what are we returning? We're returning n. Because if we return n, we can ensure that the pointers stay together. And if you're confused on how that happens, refer to my video on binary search trees, where I actually go in depth about the binary search tree code. Okay. Now we can focus on rotations. What were the rotation cases? There were 6 of them, right? L1, R -1, L0, R1, R -1, R0. So we are here in this remove code. Here, so removal actually occurs. And then just here is where we want to handle rebalancing the tree. Or should it be here? No, it shouldn't. Think about with insert, where do we have the balance factor stuff? At the very end, because balance, it'll affect the whole chain line, right? We need to calculate the balance factor for the whole chain line. If I just focus on where we're removing, Is that going to affect the whole chain line? No, it's not. We're not going to be in this else case for every single element. So then, where are we going to handle this? Right here. So what do we need? First, I need that balance factor. So we'll call our balance factor, passing an n. And then if our balance factor is less than or equal to, so if our balance factor, first case, if balance factor is 2, obviously, this is when we have an imbalance. So in balance factors, we can say balance factor of n dot left. So when our left child's balance factor, so what are we doing right now? We're doing L1. So this is less than or equal to 1. So I'm just going to say in the 0 case, L0, just do LL rotation. So n is going to be equal to LL rotation of n. Else if balance factor n dot right, or here, we can simply just do this in else. N is equal to RR rotation, LR rotation. Do we have to delete anything here? No. Why is that? Because we've already handled deletion here. All we're doing now is, okay, we've deleted the node, let us rearrange the tree and its elements. Else, so balance factor is not 2. We actually want to say else if balance factor is -2, right? This should not be a catch-all situation. If balance factor of n dot right, if this is less than or equal to 1, let us perform our RL rotation if necessary. Else, we can extend it to full RR rotation. So really, we're performing RR rotation and LL rotation twice. Oh, yeah, I did make a mistake. Actually minor ones. Hey, we're coming around, bro. Compared to the freaking 70 trillion errors I got for insertion, bro. And these are simple. Look, this should return null. I don't know. I created a new node, had insertion on my mind. This is deletion. When the node is not found, return null. What else do we do? This is fine only. Oh, I did mess these up, unfortunately. This should be greater than equal to 0. Okay, just look. What are the cases here? What balance factors trigger LL rotation? We can either have 0 or 1. Oh, we won't have 2. That would trigger up there. Because also n dot left is fully fixed right now if suppose a problem. Anyways, right, we need only these cases. If it's less than 0, so -1 should go here. Same idea here. This will handle 0, 1. This will handle -1. I messed them up, mixed them up a little bit. Because when I had this line here, sure this would have captured 0 and 1, but guess what? It also captured -1. And -1 shouldn't go to LL rotation, it should go to LR rotation. And then there's one last thing we need to do is we need to constantly check the height of the tree, right? In insertion, even though some nodes heights never changed, we still need this code. So I'll just put that here. All this code does, and we explained it in the other example, right? It's very important, so I actually want to explain it. We use it in here both. Let's just write that here, should be fine. Excuse me, because this should run regardless of these cases. This should run for every single node. Excuse me. So this is the remove code. There's one last bug in my code. I'm just a dunderhead, bro. Why am I doing n dot left dot right? That's gonna give us the old root. We want it to be the new root. It's just n dot left, n dot right. But that is the AVL tree. I hope you learned alongside of me because I learned a lot while coding this tree. I think it's interesting. I understand binary trees a lot more now. The rotation cases I like the most. I like what we did. I think this was fun coding. And hopefully you understand height. Hopefully my explanation made sense of this line, which you see so much right here. Why is it here? Because the height children change, right? Whenever your children themselves change, when has more children, when has less children, we should refactor height. We should check height because somewhere along the lines height will change for some element in that code. This is why we check height. This is why we check height. Because children will change here for you, and you will change your children. Your will have new children. Your returner will have new children. Same idea why we check height here. Not everything will change, but something should change. Like your height would lower at one point. We need to then update the height for every single code or every single node. Yeah, okay, cool. So that was AVL trees.